Swayam Prabha. Digital India. Educated India.
Okay, so you may be by now are familiar with the chemical bonding concept, right? Okay, mostly. Don't know whether I can. Can I change this with this or? Okay, fine. I can press it. It's not a problem. Okay. 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 So, I mean, it is customary for the lectures of this kind to ask a question, right? What is chemical bonding? Just want to know what you know, and therefore we can start from that step. Bond between two atoms. Okay, write it down here. All your answers. Bond between two atoms. Okay, next. No nuclear involved. Okay, both are involved. Yeah. Just tell me answer so that we can try to refine this. Okay. Have you heard of covalent ionic bonds? And then have you heard of molecular orbital theory, valence bond theory? Have you used them? So what did you use them for? Bond order calculations. Yeah. So you take, let's say you might have seen this picture, right? Okay, have you seen this picture from your molecular orbital? What is this? Okay, just from this pictorial representation, irrespective of your quantum mechanical knowledge, can you define chemical bonding? Or just at least can you phrase what actually is a chemical bonding? Just from, you have some picture in front of you. I ask you to actually give it a language. Yeah, bonding, anti-bonding. So what is meant by a chemical bonding then? Molecule. Yeah, that's how you see this, right? Yeah. Okay. So by the way, this is the electronic density around this. Okay. Yeah. Yeah. So in the situation what you call bonding, there is an electronic charge density accumulated between the nuclei. Okay. Only then you have a bonding situation. If the electronic density is thrown out of the region between the nuclei, then you get an anti-bonding situation. That's what is this case, right? You have no accumulated charge, the electronic charge between these two nuclei. It's like electronic density acts as a glue to these two molecules. Yeah. So this is familiar picture to you, right? EMBO theory. Yeah, we don't get into that. Okay. So what did you see here? You have, let's say, two hydrogen atoms combining to form hydrogen molecule, right? It's kind of a reaction. I draw an analogy to the reaction, chemical reaction, okay? Okay. So you have reactants and you have products. That's what the static aspects of chemical bondings deals with, okay? Linus Pauling, Lewis, who else are familiar with, are masters of the static aspects of chemical bonding in the history? Hitler, London, who developed MOT, by the way? Is it Hitler and London? Or is this valence bond theory? Who developed valence bond theory? Who developed molecular orbital theory? Hitler and London? And then MOT? Yeah. So it's kind. I mean, it's a more or less. There are common set of scientists who developed both. Okay, but historically these two theories were like main contenders to describe the bonding in molecules. Okay, but sometimes one fails, the other wins, and then it's vice versa usually. So the question for you here: can you just tell me where MOT fails and VBT is successful, and the vice versa? Some examples. Yeah. So MOT predicts the properties of oxygen, the paramagnetic nature of the oxygen molecule, right? Because as you start filling these molecular orbitals using Aufbau-Hund's rule, and then taking into account implicitly the Pauli exclusion principle, right? Because two electrons have to be paired up in a single orbital. That's Pauli's exclusion principle. And then you kind of get two unpaired electrons here in some pi star orbital, and that explains the paramagnetic behavior of oxygen, right? Whereas in VBT, does this picture fails, okay? It doesn't, it kind of takes Lewis dot structures into account and then try to fill it around two oxygen atoms. So all the electrons have to be either paired or bonded, okay? Whether it's a lone pair or not. So you won't have single. So I just ask you to actually write down the Lewis dot structure for oxygen, O2 molecule. You have an idea, right? You can write it down. Just see whether you can, whether the VBT, which is actually a quantum mechanical extension of Lewis dot structures, can predict the properties of paramagnetic behavior of oxygen. Okay. So it so happens that this theory fails and this theory is successful. Okay. There are cases where VBT is successful and MOT fails. You know that? Any idea? Yeah. Okay. Try to explain the bonding of C2 molecule. Okay. But our main interest is not in appreciating the static aspects of chemical bonding. I just want to briefly discuss here just to give a flavor of what actually chemical bonding is, and this sets further stage for us to describe the dynamics of chemical bonding. What does it mean? What does it mean? So you see here already you have a reactant ended up forming product without any due regard for the process of formation, right, in time. That means it would be like, if I imagine it, that I have two hydrogen atoms. First, they would be like, they are kind of separated at a constant distance. So the spherical shapes of these two orbitals are somehow disturbed and be some sort of ellipsoidal shape they take, and then finally these two, let's say time t0, is at some time t1, okay. And then it could be that they start significantly overlapping and then finally taking to okay. But this sort of static picture of chemical bonding doesn't explain this dynamic transformation of these atoms to molecules, right? So we are going to focus on how to observe the breaking of chemical bond and formation of chemical bonds in real time. That means as this process happens, how do you see these, whether the atoms are coming close by or leaving apart from each other, okay? Okay, so what is the time scale that you think of kind of required here? What is the time scale that goes on here? Because it's, you have seen that nuclei are approaching and the electronic clouds are deformed. So what is the time scale, typical time scale associated with this process? Your guess, I mean, just you can guess. Are these electronic motions in molecules and nuclear motion vibrations in molecules happen at the same time scale, roughly? What are the typical time scales of electronic motion? You heard of this term femtoseconds, right? And you also heard of attoseconds, no? Right? What is 1 femtosecond? Minus 15. When you say this, do you have any feel for this number? I mean, or you are just saying that, so this 1 second, okay? What is the age of the universe? Maybe we just to give a feel for this number, what is the age of the universe? 32 billion years, I think, approximately. Yeah? And 1 second, we can perceive that, right? 1 click in the clock, right? So 1 second is to the age of the universe is like 1 femtosecond is to the second, okay? You can now imagine that the time scales, okay? But can we see the processes happening at this time scale, for instance? Why not? Any idea why not we see that? I mean, just, okay, without any instrument, just with our bare naked eye, okay? Can we sense this, just see the processes happening at the time scale? What is the reason? Too fast. So how fast? I call it ultra fast, okay? Okay, we reserve processes, ultra fast time scales as being the femtosecond time scales, okay? So femtosecond time scale here, it could be anywhere between not just 10 power minus 13, 15, minus 13 to typically within this range, okay? Yeah. So both the electronic motion and nuclear motion happen to fall typically within this time range, okay? In real chemical systems of interest to chemical bonding, okay? So there are cases where electronic motion is much faster than this time scale, which is slightly an order of an order of magnitude less than 10 power minus 15, let's say 10 power minus 16 seconds, which we call attosecond time scale. Okay. You can also view the chemical bonding from the perspective of the electronic motion or from the nuclear motion. Okay. As the nuclear approach, electrons are kind of reorganize quite fastly, so that we don't have to worry about the reorganization of the electronic subsystem here in the molecules. We just can see how, with what velocity the nuclei move towards each other, and then with what velocity, with what rate, or with what time scales they move apart. Okay, because there should be some critical distance between the nuclei, right, to form a bond. Yeah, so that's you're familiar with that this kind of graph, I guess. So we just wipe it out. Okay, so have you seen this graph? The following one. What is the x-axis? Let's say if we put that in here, okay, apply it to the hydrogen. Yeah, I call it potential energy. Okay, why do you call it potential energy? Any reason? Potential of electrons, that's correct. Okay, we'll try to make it more rigorous, okay, as we go along. So you have this Morse curve, which kind of summarizes the bond formation, right, from the bare atoms, which are somewhere here. Right. So we are interested in actually the motion of nuclei as they approach each other and as they depart from each other. Okay, and then in this motion occurs, as we have seen. You can just calculate the typical vibrational period of your molecule, right? What is the typical vibrational period of your molecule? Yeah. Let's say, any of the frequencies that you are aware of any molecule. Any typical frequency, vibrational frequency. Okay, if not aware, we will see them. Okay, we'll see them. For now, you take note of the fact that the vibrational period is of the order of 10 power minus in picoseconds. Okay, 10 power minus 13 minus 12. Okay, so we are interested in the breaking and making of between okay, and the glue here is the electronic one. Electrons are anyway fast enough to readjust to a given nuclear configuration. Okay, yeah, okay, fine. So with this, I formally begin our topic of today. So this is, those who are interested in this can take this. Okay, so this is the situation that we have actually described using orbitals. The fact that you brought in orbitals implies that you are already dealing with quantum mechanical phenomena. Okay, yeah, orbital is the one electronic wave function. Let's say, imagine that the radial distribution functions, the 1s wave function the radial distribution, e power minus r by a naught. Anybody remember? 1s orbital of hydrogen. So it looks like this. That's the, so you have two hydrogens. So e power minus, the wave function is proportional to e power minus r by a naught. Okay, in one dimension it turns out to be x by a naught. If you plot this, this is how the wave function looks like. Okay, and then let's say this is the nucleus of the hydrogen atom, and then the wave function spreads like this. Okay, in one dimension. So it so happens that this goes to 0 almost at 400 picometers. But you see here the wave function here extends to this nuclei, the wave function here extends to this nuclei, right? Because that's because the usual separation between these nuclei is around 70 picometers. The wave function still doesn't vanish. Okay? And then when you add these two, that's what molecular orbital theory says. It tells you to add these two orbitals, linear combination of atomic orbitals, and then form bonding. The in phase addition. Okay, it's called psi a plus psi b, gives you this one, psi b. And then square of, I mean, what is important to us is the square of this wave function, which gives you the probability density associated with this electronic wave function. So you see the probability density is kind of concentrated here between the nuclei. You do the same wave function and do it as a anti-phase addition. Okay, psi a minus psi b. So you kind of flip this and then add it. So you kind of get a node here, and then square it. So you have almost 0 probability density between the nuclei. The probability density is thrown away from these nuclei, right? In other words, away from this region. Okay, that's called anti-bonding situation. Okay, so I mean, this is just to make you aware of the fact that we are dealing with a quantum mechanical phenomena. Okay, the chemical bonding concept is completely okay. Okay, once this is done, okay, so we have talked about the time scale associated with the electronic motion. If you see this picture, you see on the left hand side you have electronic density reorganization, which is happening in 2 femtosecond time scale, right? On the right hand side you have a bond that's broken and then formed between two rings. Yeah, they're kind of closing together. That's happening around 150 femtoseconds. That means 2 orders of magnitude slower than what attochemistry is. When if you just see the bonding from the perspective of the electronic reorganization, you have to resort to second time scales. And on the other hand, if you want to see the reorganization of the nuclei involved in the bonding, you just have to resort to femtochemistry. That means 2 orders of magnitude higher time scales. Okay? Yeah. Okay. Sorry. Yes. Okay. So you see here, so this is like, I mean, you have an orbital kind of thing, right? Or you kind of squared these orbitals and you got electronic density spread over the molecule. There is some tip, I mean, let's say I think it's the same molecule. Yeah. And then you kind of perturb this electronic density with a laser pulse. We'll just talk about why do you need laser pulses and things like this. Okay. If you perturb this electronic density, and then it kind of is going to be reorganized in some crazy fashion like this. Okay. So as a result of this reorganization, there will be eventually some bonds broken, some bonds formed. Okay. That if you would like to view this chemical bonding from the perspective of electronic motion, you would have to resort to attosecond time scales. On the other hand, you just kind of don't worry about the electronic motion, you kind of just come up with a laser pulse which is of femtosecond time duration, okay, the red one here. So what happens, you hit this bond here, you break one bond and then you form another. In other words, you kind of let the two nuclei move away from each other, we'll see how it actually does, okay. And then wait for some time, then these two rings come together and slowly form this bond, okay, on 150 femtosecond. Okay, so here the energies associated with electronic motion and nuclear motion are given in electron volts. So, and the time scales associated with electronic motion and nuclear motion are given as we discussed, okay. But the caveat here is that we are actually talking about electronic motion and nuclear motion individually, but in real molecules, these two motions are highly coupled, okay. The kind of electronic degree of freedom often talk to the nuclear degree of freedom, and then nuclear degree of freedom vice versa do that. And there is a time scale, both of these motions can compromise. That happens somewhere between 10 power minus 15 to 10 power minus 14, okay. We'll talk about such phenomena, okay. We are mostly interested in the femtosecond regime. Okay, so these are some of the literature. Maybe you might be knowing this personality, right, Ahmad Zivel. How many of you heard, have seen, have you heard of femtochemistry term? Okay. What is meant by femtochemistry? You don't have to define from the knowledge, from what we discussed, can you just guess what is meant by femtochemistry? Yeah. The fact that we are talking about chemical bonding, we are talking about chemistry, right? Breaking and making of bonds. And then if it happens on femtosecond time scale, and then you tend to observe it using femtosecond laser pulses, you call it femtochemistry, okay. And the father of femtochemistry is this person, Ahmad Zivel, okay, who got the Nobel Prize in 1999 for his discovery of femtosecond laser pulses, and then exploitation of these laser pulses to the study of chemical bonding, okay. So there are some books written by him. Maybe one is the chemical bonding static and dynamics. That's kind of more like edited volume. Many scientists contribute to it, each chapter of it, and then he edits it, okay. And then some video talks, you can listen to it, and there is a beautiful review in in Journal of Physical Chemistry, femtochemistry. You would like to read it, okay. And then some textbooks, and this is one of the classic textbooks I found, Tanner's Time Dependent Quantum Mechanics, okay. If you would like to, I'll provide you full description of the title and other things. You can buy it if you wish, okay. So, why study chemical bonding? Try not to read this and answer this. You understood what is chemical bonding? You kind of understood on what time scale it happens, and then you also sort of understood what is required to actually probe this chemical bonding, yeah, as it unfolds in time, okay. We solidified these, we are going to solidify these ideas as we go along, okay. Before that, why do you need to study chemical bonding? Yeah. Okay, you have reactants. How many of you are interested in organic chemistry? Have you performed reactions in your practicals? So what did you do? You added reactants? Yeah. So you kind of maintain the temperature at atmospheric pressure, right? And then you kind of control the reaction with the concentration, temperatures and things like that. You form the products and you're happy, right? So you have reactants and then products. You wanted to go from here to there with highest possible yield and then the fastest possible scale, right? So, but you already know that there is some transition state possibly somewhere here that is actually in between the on the way to reaction, on the way to reaction, on the way to products, right? So what do you call this? Transition state. Yeah. Okay, let's say if these two, I mean this whole path, for instance, is let's say 10 angstroms, okay? The reactants and products are separated by 10 angstroms on this path. By the way, what is this profile? What is this profile? Yeah? Energy profile. What energy is this? Is this potential energy? So this is the same potential energy that we have seen, okay? Yeah? Okay. And then this is reaction coordinate, people call it, okay? So what is meant by reaction coordinate? Let's say if I have a molecule of this kind, I want to break this bond. What would be the reaction coordinate? So I would take OH as my reaction coordinate, okay? How many modes are possible for this molecule? Vibrational modes? You have any idea on how to calculate vibrational modes for for linear molecules and nonlinear molecules? Okay, good. Yeah. 3n minus 3n minus 5, 5 for linear. 3n minus 6 non-linear. So how many modes, vibrational modes for this molecule? How many atoms are in here? 40. Okay, so definitely more than benzene, right? Because you have two extra atoms, so oxygen and hydrogen. Yeah? Okay, fine. Benzene has 30 vibrational modes, by the way, and it should be higher than 30. All the vibrational degrees of freedom except ROH, I mean the vibrational degree of freedom that is mimicking OH, are going to be perpendicular to this coordinate, okay, and then contributing to this potential energy. In that case, you will get a multi-dimensional potential energy surface. Okay, this V is going to be simply function of all those coordinates. Okay, until Q40, along with this ROH. Okay, we get a multi-dimensional surface. But all these coordinates may not be contributing to or promoting the reaction. Okay, some of the coordinates may be mere spectators without contributing to the reaction. Yeah. So therefore, you can ignore. I mean, you kind of take only the relevant coordinates and try to understand your reaction mechanism. Okay. Now, before this is just small digression just to explain what reaction coordinate is. Yeah. So let's say if the reactant, I mean, if this landscape connecting the reactants and products is with this distance. Yeah. I mean, the extent of this landscape has 10 angstroms. Okay, the spatial extent. If the reactants, I mean, what are the typical thermal velocities of molecules? Any guess? So you can just calculate thermal velocity with this, right? kVT by the mass. So you can just start with hydrogen atoms and then try to calculate, estimate. It's of the order of let's say anywhere between 300 to, depending on the mass of the molecule, 1000 meter per second. Okay, it depends on the mass of the molecule. Suppose let's say I take 1000 meter, I have heavy atoms here. I take the velocity of the reactants being 1000 meter per second at room temperature. Okay, so velocity of these. Now you tell me how much time would it take for the reactants to go to products if the velocity, if their velocity is 10 meter per, 1000 meter per second, and if these, if they extend, if they have to cover this distance, 10 angstroms. What is the time required, let's say, for the reactants to go to products, crossing this, this 10 angstroms with this velocity? Yeah? 10 power? Minus 12 seconds, yes, 1 picosecond, okay? One picosecond. Okay, so then if a reaction process happening around 10 with 1 picoseconds, you would need a kind of camera that can take the snapshots when the reactant is here, when it is here, when it is here, it is here, and so on, right? And this process takes 1 picosecond. You need a camera that kind of quite quick enough to grasp all these snapshots before the reactants go to products. That means it should be less than, the camera shutter speed should be less than 10 power minus 12 seconds. Yeah, it should be much faster. Yeah. So you would then need right? Yeah. Then kind of on the way, I can keep a camera and then click all these frames and then combine them to have a movie that reactants are approaching and then slowly forming a transition state geometry and then leaving apart and things like this, right? Then you can study. And what is the advantage of studying such chemical acts? So you have in organic chemistry performed your reaction without any due regard to what's happening in between, right? You kind of macroscopically try to control the pressure, the temperature, concentration of your sample in order to make the product yield better and the reactant rates faster, right? But how come this microscopic detail help you better design your reaction? Can you connect these two? Now, if you know that how the reaction proceeds, what are the geometries involved at various points of time, can you exploit this to controlling your chemical reactions in laboratory? How come? So how do you want to exploit this? Let's say you have now a movie of this reaction and you are given in the lab these reactants and you would like to actually control with this mechanism in mind the product formation, the yields and rates. How would you exploit this? Yeah. Okay, we'll be able to answer this by the end of this lecture. Okay, for now you keep it in mind. Okay, that's the holy grail of chemistry. If you can do so, with the help of lasers, so you are kind of doing laser selective chemistry, right? Kind of excites, it kind of cleaves certain bond and then makes it faster. Usually the temperature and the concentrations, what would they do? They kind of non-statistically, it's kind of statistically distribute the energy between all the modes. Once you put in energy, the energy gets wasted due to the statistical distribution. So therefore, you would like to control that by taking precise scissor and then cut one particular bond. It's like using laser pulses you are kind of depositing energy to a particular bond and then breaking it, and then it becomes much more efficient and clean, right? Yeah. So we would like to avoid so-called intramolecular vibrational redistribution in reality by resorting to such short and short laser pulses. Okay. Okay, that's the holy grail in chemistry. Okay, the challenging aspect, chemist's dream of controlling chemical reactions. Okay. So I mean, when you calculate rate, for instance, okay, you have a reaction, first order, second order reaction. You can calculate rates, right? And then what is the Eyring equation? Can you tell me? Eyring equation to calculate the rate, unimolecular rates. Okay, it is something to do with the partition functions. I mean, if you are aware of that partition function, statistical mechanics. Otherwise, just okay. You have rate constant in terms of the concentrations, right? And then you also have this temperature effect because there is a factor sitting here by H in the rate constant. If you go back and see Eyring equation to calculate the rate of a unimolecular reaction, you would see these factors, temperatures, concentration and all. So that's what you are actually doing. You are trying to enhance the rate by increasing the temperature and then making it faster and better. But the microscopic details are completely lost here, right? You don't know what individual molecule is actually doing. Yeah. So in femtochemistry, you can actually make a movie of these individual acts, the acts of molecules at a given instant of time, okay? And then see, is this the reaction mechanism that's happening? You can kind of conclude it, okay, from these experiments. Maybe I'll just show you one example where people can imagine things and then turn out to be wrong through experimentation. Am I missing something here? Yeah. Okay. So this was the Ahmad-Zivir, okay, we were talking about, and then he kind of in 1980s developed this femtochemistry field, and then got a Nobel Prize in 1999. Okay, and then this was the reaction involved. What did he do? You see here, there is a reaction, sodium iodide, which has covalent and ionic characters. So he kind of observed when this molecule is actually covalent and when it is ionic, and then when it is oscillating between these two structures. So that's what he has done. We'll talk about it in the second session, okay? And then he kind of observed these oscillatory behavior in the pump probe signals. He performed so-called pump probe spectroscopy, which we'll talk about it. And then these oscillator signals infer something, okay, about the nature of chemical bonding in sodium iodide molecule. Yeah. So as I was talking about, we have drawn that transition state diagram, right, which looks something like this. You see reactants and products, and then there is a transition state here. Okay, maybe I'll. You see transition state, reactants and products. Actually, this is just simply a potential energy cut from a kind of multi-dimensional surface, because as I was writing here, if your molecule has as many degree of freedom and your potential can be the function of those many degrees of freedom, right? So here in case if you have a two-dimensional potential, you would have to draw it in 3D. Yeah, two-dimensional in the sense it's a function of two coordinates, okay? So you would have to draw it in 3D, and then the reactants are somewhere here, and you would need to go to this well, from this well, right? So how would you go? What is the least energy consuming path? So it's like a hill, right? So How would you take this path and then go here? I mean, you just can stop over for some time here, or would you try to take around the hill, which is a minimum energy path, which is less effortful, right? And then reach this path and then reach these products. In doing so, I mean, molecules also are clever and they take this minimum energy path, okay? They kind of go around the hill. Suppose if you, so this is a situation, right? So it's like, yeah, it's like, so you have your reactants and somewhere here your products, right? So I would like to go this way. That's a minimum energy path. I mean, the molecules also prefer that way, not this way, right? Yeah. So if you take such a cut, okay, that turns out to be something like this. Can you see that how it turns out to be? You see here the transition state here, maybe. So there, as you go from reactants to products, you encounter a kind of slight barrier along this reaction mode, and then this barrier turns out to be minimum, okay, along the other reaction coordinate. You know, I mean, how many of you have seen this horse pedal, the sitting pedal, right? So have you the horse pedal, the sitting pad in the horse. So it kind of, in one direction that you have a minimum, in the other direction this is a maximum. That's called first order saddle point. So transition state lies exactly that the intersection point, okay. In one direction it's maximum, the other direction it's minimum, okay. Only along the reaction coordinate it turns out to be maximum. In all other directions it turns out to be minimum, okay. Okay, this is just the 2D representation of the same thing. You kind of chop it up and then project it in on the 2D dimension, and then kind of, it's like going from here to here is like going from this well to this well via this minimum energy path here, okay. Yeah, so in the construction of such potential energy surfaces, we assume so-called Born-Oppenheimer approximation. How many of you have heard about this? So what does it say? Proton, total energy equal to translational plus vibrational plus rotational plus electronic. Okay, I mean, Born-Oppenheimer approximation simply assumes the fact that the electronic and nuclear motions are separable because of the time scale associated with each of these motions. Electrons happen to be moving much faster because of their lighter mass compared to the nuclear mass, right? Therefore, they have different kinetic energies. So that means different time scales of motion. You can kind of treat them separately, yeah. So to get this potential energy surface, okay. So when do we need to take the break? Around 3 o'clock, right? Yeah. Okay. Just tell me when you need the break. How many of you are familiar with this equation? Schrodinger equation, right? Time independent Schrodinger equation. There is no time here. What about this equation? Okay. I write all the variables in 1D. So this is a time dependent equation. You can get this equation from this one, right? And then you call it time independent. That you know, we don't variable separation method, and you can get this one, okay? Since you mentioned it's time independent, there is no time in here, only the space part, okay? Okay. So in other words, it's the part of this total wave function. Okay, now here how does this Hamiltonian looks like? The Hamiltonian that's in here. Okay, the molecular Hamiltonian. We are talking about the molecular. How does it look like? You have two objects, right? The electrons and nuclei, and they move. They have their respective kinetic energies. So I write it. Kinetic energy of the electron, kinetic energy of the nuclei, plus, and they also interact with each other, right? Electrons interact, and then I call it the potential energy of the interaction of the electrons, plus nuclei also interact, right? And then nuclei and nuclei also repel, they also interact. The potential energy associated with this, right? So Born-Oppenheimer approximation tells that you put it to 0 and then approximate your Hamiltonian. Only there are 4 terms left, right? TE plus VEE plus VEN plus VNN. And then you call, you see, mostly it's kind of electronic dominated, right? And then when you put it to 0, that means you are actually freezing all the atoms artificially, no? Which means that you know the positions of individual atoms. You can, since if you are doing it theoretically, because this is a theoretical concept, okay? So you freeze all the atoms, you kind of can calculate the nuclear repulsion and add it to the Hamiltonian. So therefore, it's kind of adding a constant here. So therefore, you call the remaining Hamiltonian, keeping this to 0, because there is a nuclear mass entering here, right, which is heavy compared to the electron mass here. Therefore, nuclei are assumed to be almost non-moving. That means they have no kinetic energy. Therefore, it is put to 0 here. Okay. The rest of the story is like the remaining Hamiltonian you call electronic Hamiltonian after keeping this 0. That's what is simply Born-Oppenheimer approximation. Following Born-Oppenheimer approximation, what we do, we solve for this equation. Okay. So I write it quite elegantly. So you have electronic Hamiltonian after this setting this to 0 following Born-Oppenheimer approximation, and this electronic Hamiltonian is function of electronic coordinates, nuclear coordinates, right? But you kind of freeze the nuclear coordinates, no? So therefore, it's like I define this with electronic coordinates, but I take the nuclear coordinates as parameters. I kind of fix that and then deal with the rest of the Hamiltonian. When I fix that, this goes to 0 and this has some value, and the others I would have to evaluate. Okay. So it so happens that E of R yeah. If I am taking R, this is total molecular wave function, okay? We are just taking part of it, which is only the electronic part. Sorry, this is R, okay? You got the idea? So we are simply taking portion of this Hamiltonian and then trying to do something here in order to get these values. So this is a eigenvalue equation. You can construct this Hamiltonian and diagonalize it. That's what all these Gaussian packages and the Malpro packages do that. You know these electronic structure packages, right? Have you heard of these electronic structure packages from your quantum chemistry classes? Yeah, no? Okay. There are some set of software packages which try to solve this equation and give for every nuclear positions, okay? In this case, if you take, so you have OH, you fix this R and solve for this equation, you get one energy, yeah, for the ground state, excited state, first excited states. So it's kind of family of states and energies you get, okay, for this fixed nuclei. Again, you vary this R and then solve for this equation, you get sets of energies. And then if you connect only likewise you keep doing for all these R's. If you connect only the lower state, lower energies, you get a plot of this kind, okay. That is what is called potential energy, because this is like you ignore this nuclear kinetic energy, the stuff is called kind of potential energy, okay. Kinetic energy plus rest of the stuff is called simply the potential energy, okay. That is what, so the energy that comes from this equation is what is plotted usually in chemical reactions, okay. And this ROH reaction coordinate means for every R you solve this equation and get the energies. You got the point? Appreciate it? Okay, fine. So hereafter we are going to we are going to see only the potential energies landscapes of this kind, and then the chemical reactions happen on these complicated potential energy surfaces, okay. So it's not simply that you mix the reactants and then see the products, okay. There are a lot of things. Okay, so some more potentials. Let's say if you would like to, I mean, you can have potentials something like this. Have you seen these kinds of potentials? You heard about Jantala theorem, right? Jantala theorem? Yeah, distortion, Jantala distortions you heard, theorems. So what does it say, Jantala theorem? Yeah. So you have high symmetry configuration of a molecule, and then it does not like that configuration, therefore it reduces its symmetry by lowering its energy, right. So this is what actually is happening, okay. The theoretical description of it is simple. So you have your high configurations sitting somewhere here, let us say octahedral geometry, okay, of some complex sitting here, this touching point, you know, see here, that is where you have the degenerate electronic states. So this is one electronic state, this is another electronic state in the space of nuclear coordinates, right. We are actually getting these potential energies as function of the nuclear coordinates, okay. Now that I have two nuclear coordinates, not one, therefore it is a surface, yeah. So you see here I have an octahedral complex, it kind of distorts itself to go to lower symmetry somewhere here, and then while doing so it also reduced its energy, right, from here to here it got dropped down, okay. So it kind of, I mean, have myriad number of configurations around this degenerate point along this whole disk, okay. So it can, there are many conformations for this octahedral system, so they all can be represented here. Anyway, so if you just take one cut from upper surface and the lower surface, so that is what is this one, okay. And similarly you can have potential energy surfaces like this. So you can just take one cut from upper and lower, they touch somewhere here, not here in the, this is like a function of some coordinate, nuclear coordinate, okay. So you can have all kinds of potential energy surfaces and their cuts. So we usually, I mean, cuts are kind of qualitatively indicate the nature of the potential energy surface along the reaction coordinate, along the reaction. Therefore, better to visualize the potential energy in terms of cuts also, okay. Okay, once you have the platform, which means the potential energy surfaces, okay, we are supposed to actually look for the other component in this wave function, right, because our ultimate goal in describing molecular dynamics is to solve this equation, okay, and the Hamiltonian corresponding to it is this whole Hamiltonian. We only have solved only for part of the Hamiltonian, and then you got part of the wave function, which we call electronic wave function, and the electronic energies. There is also another component in it, right. Molecule is composed of both nuclear and electron. There should be a nuclear component also, which is missing. So if you kind of do some algebra, and then you can reduce this equation to simply, I call it chi HEL, this portion plus the leftover portion previously, okay. Okay. So finally, I have solved for actually the electronic portion of the packet. This actually is composed of the electronic portion times the nuclear portion. Okay. Okay. We have solved it for this portion. So now the nuclear wave function, one needs to solve for this. Okay. When you put these answers into back this, then you get an equation for this, exploiting this. Okay. So you see here the energy of HEL, the eigenvalues are here, right? It naturally enters here. So it's like you have a potential energy surface and you add the missing kinetic energy to the problem and you solve for this equation, the chi, only the function of nuclear coordinate, capital R, right? And this is called nuclear wave packet. Okay. So now you see here, you have the potential energy landscape. You see these two surfaces, this one and then this one, which you calculated by solving this equation. These are called electronic potential energy surfaces because the solutions of this equation are electronic states and electronic energies for each R. Okay. And then use this as a potential energy for the propagation of nuclear wave packet. Propagation means the solving the time dependent Schrodinger equation for the nuclear wave packet. That's what is it. In other words, these are kinds of platforms for the nuclei to dance upon. So these are nuclear wave packet, these are electronic states. Okay. So the simple Jablonski diagram that you are familiar with, writing S0 with some levels, well separated from S1 and things like this, no longer is applicable in chemistry, okay, particularly in the excited states. Okay. So therefore, all your chemistry relies on these kind of complicated electronic energies. Okay. It's not like you have a molecular structure and it has electronic states. This molecular structure is dynamic. It's always kind of the nuclei and electrons are in constant motion. Okay. So therefore, you would have to describe the motion of the molecules on these complicated surfaces, electronic surfaces. So the nuclear wave packet, when you solve this equation, it kind of gives you an impression that, okay, so when they touch here, there are two electronic states. When you launch your initial wave packet here, it's like a funnel, no? So the nuclear wave packet, simply part of the nuclear wave packet goes in here and the remaining part is here because it's quantum mechanics, no? You cannot assume that all the wave packets zips through, right? So this eventually happens, again it goes back and then it falls into this well, amplitude slowly leaks through, okay? It takes some time. So this is the premise for chemical reaction dynamics, okay? Having potential energy surfaces, evolving nuclear wave packets, using that equation is what defines the chemical reaction dynamics. You see, the location of this wave packet should clearly tell you what is the molecular structure associated with the location of this wave packet, because these potential energies are simply functions of nuclear coordinates, right? You are fixing the nuclear coordinates, particular geometry, and you're kind of obtaining this. So at every point on this potential energy surface, you know what the molecular geometries are. So if you track the evolution of this nuclear wave packet, you're kind of tracking the molecular structures possible, right? And it has to be done in femtosecond time scale in theory. In practice, you see how Zivel has done after our break, okay? And for instance, I'll just show you one more simple example. It's like photo dissociation of water. So there are two potential energy surfaces for water, then you excite it, and then it also has this kind of intersection point that's called conical intersection. It looks like a cone shape, no? Yeah, that's called conical intersection. Okay. So it slowly kind of, it can form this product. When, I mean, initially it was excited to this electronic state and then it rushes through this. Why should it go this way? Why not this way? The wave packet, yeah? Yeah. So this is something that you have to think. We'll just reveal it in the next class, I mean, the following class. So it moves this way and then comes back this way, and then as it moves and comes back, it leaks through, okay? And then when it leaks, it kind of has two pathways, so it can dissociate to this product or this product and things like this. So you can find in this paper the details of H2O photo dissociation. This just to make you familiarize with the potential energy surfaces, because we are going to rely on these surfaces in order to you can have much more complicated potential energy surface. It's by phenol. We have done phenol, right? The OH coordinate. Actually, these potential energy surfaces you see here as function of OH. So you see we have drawn that Morse potential, right, in the initially. So that's this Morse potential, but in 2 dimensions. Yeah, there is also another coordinate here, which is like OH can rotate with respect to this phenol ring. That's the degree of freedom that's taken here. So you see here the ground. This is ground electronic state. The orange is the first electronic state, and this one is the third, the second, and then the third. So when you excite the molecule to these states, you can have a dissociation products formed in this state, here in this state, in this, because when you are here already, the OH is already broken, right? It's almost 2.5 angstroms. That means it's already broken. So when you are here, it's the stable phenol configuration. When you are here, it's this bond broken already. Okay, that's what these potential energy surfaces kind of give you an impression. Okay, then we'll just after coming back, we'll talk about why do we at all need laser pulses, yeah, to excite or to trigger this molecular reaction dynamics, and then what Zivel did in his experiments. Yeah. Okay.
SwayamPrabha, Digital India, Educated India.